modeling problem that is on the accumulated amount if you were to indulge in an investment scheme that returns compound interest. Okay, so I believe you will know lah, right? I think you should know what is the meaning of compound interest, right? Compound interest is just interest that compounds on the previous interest. Okay? So actually, we can repeat the same kind of analysis as similar to the pandemic COVID-19 virus spread that we have gone through in the lecture, right? And then come up with the same differential or difference equation, okay? And then we'll be also able to deduce the solution of the accumulated amount, and then also we just try to apply that solution, right, to some investment, actual investment, and then we see we can get the nice amount of money that we have there. Okay? So let's look at question 5 here. Okay, so the tabulation is actually quite similar to what we had for the pandemic. So basically what we want is the T in terms of years, so year T, and then you want to have your accumulated amount, so accumulated wealth, which is A of T, okay? Then what is this? This is the difference, right? The difference is the increment, okay? So we can say that this is the difference in the accumulated amount per year. So therefore you can treat this as delta A over delta T, change in A over change in T. Okay, so certainly tabulation is indeed one way to derive the governing equation. Okay, so of course most of the time we will be applying conservation laws, right? But in some cases we can also apply tabulation. Okay, so the thing is like that lah. So in year T, right, I mean in year 0 you start off with an amount that is the principal. Okay, so you only have principal P, right? How much you invest, for example. Okay, then what about in year 1? Now in year 1, because you got to get the principal and the interest, what? So naturally it must be P plus the interest rate or the return rate times P. Agree, yeah? P plus RP. Very straightforward. Okay, because you still have your principal. So therefore, what you can observe here is that this is actually equivalent to 1 plus R times P, or P times 1 plus R. Agree, yeah? Okay, so then what is the difference in the accumulated amount from year 0 to year 1? Then it's so easy, right? It is just RP because you got the interest, what? So this is actually your real return. This is your return for year 1. Okay, or rather return after 1 year, if you will. Can So I think so far so good, I hope. So now, what about when you have year 2? Now year 2 you must understand that it is the interest built on this amount. Now the other way, very simple, to see it, right, is you are always getting 1 times, that accounts for your principal, plus R times, that accounts for your interest. So it is always 1 plus R. Okay, it must be always 1 plus R multiplied by the amount last year. Keep in mind that. Because you have your principal, that's 1. You plus R, so you have your interest return. So therefore, you can see that for year 2, right, you're going to get a 1 plus R multiplied by the amount that is for the previous. Okay, because it's always 1 plus R times, right, of the earlier amount that you have, okay, at the beginning of the year, for example. So this is easy to see already. So this is really just P times 1 plus R to the power of square. Agree, okay? So what is the difference? Now you notice that this difference is always the interest amount. Okay, the interest that you get for that particular year. Okay, so for year 2, right, what is the interest? The interest is, or rather, what is the, what do you call that? the difference amount here. So the difference amount, right, is you can take this accumulated amount minus this accumulated amount. Agree, yeah? So you can work out quite easily. So you notice that you have P times 1 plus R whole thing square minus P times 1 plus R. So I'll work out just one time and you'll see the trend going forward, okay? So this is really just P times 1 plus R multiplied by 1 plus R minus 1. So nothing much. This one I just factorize out P times 1 plus R will do. Okay, so you can realize that this is really, right, P times 1 plus R times R, right? Because 1 minus 1 is 0, right? So you have this, okay? So you do notice that, right, this is the principal for the previous year. This guy is the accumulated amount for the previous year. And this is the accumulated amount, right? P times 1 plus R for year 1. Agree, So let me underline, So you see, year 1 you have this accumulated amount, okay? And the difference after, rather at the end of year 2, right, is always the interest multiplied by the previous accumulated amount, okay? So there's something that I mentioned earlier. So you do see this appearing here. So if you compare apple to apple, right, you'll notice that when your principal is P, you have RP. When your principal is P times 1 plus R, you have R times P times 1 plus R. So what I'm trying to say here is that it is always R times A, okay? It is always the interest rate R, right, multiplied by the earlier accumulated amount, okay? So I think we can go project ahead to year T already. So in year T, the accumulated amount must be what? Must be P multiplied by 1 plus R to the power of T. Because every year, right, you just increase the exponent of 1 plus R by 1 because you are just multiplying by 1 plus R, right? You always get back your principal, that's 1, and you always get back the interest multiplied by the amount that you have previously. Okay? So therefore, this is really the accumulated amount, right, at year T. And the difference equation, right, or rather the difference here is always change in A over change in T, must be always equivalent to RA. This will not change. So you can see that this is also equivalent to RA. Okay? So it is always RA. Okay? It's always the interest rate multiplied by the accumulated amount, right, at the beginning of the year. Okay? If you like, right, you can put it as A times like the accumulated amount at T minus 1. Okay? But it doesn't matter. Let me just put it like that. So, which means this is your accumulated amount. So for compound interest, right, you have A of T. This is your solution. It will be P times 1 plus R to the power of T. Okay? And this is your difference equation. So the difference equation is change in accumulated amount over change in the number of years, right, will be always equivalent to RA. Any questions with the derivation of the difference equation and the solution? Okay, so you might have heard that compound interest will return you an exponential trend on your investment. Okay, so in fact, if you look at the graph, right, and if this is T, so you always start with your principal at T equals to 0. That's what you have initially. And it's going to compound, okay? Because the 1 plus R is a positive number. I mean, it's not just a positive number, it's a bigger than 1 number. Number that is bigger than 1, okay? So once you have the T at the exponent, it's an exponential function. So exponential growth in wealth. Is that all right? Okay? So we should try to invest in something that will give us the exponential growth in wealth. Okay? That means we make use of the compounding effect, if you can. All right? So let's look at the other part of the question. Deduce the solution to the DE, so that's done already. Okay, and then hence predict the amount of money that you will have after 40 years if you have invested 50K initially, given a guaranteed annual interest of 5%. Okay, so of course 40 years is a long time. Okay, but I'll tell you later on why it is actually reasonable, right? So this is our equation. So which means that after 40 years, you want A of 40. So that's equivalent to your principal P, which is 50,000, times the interest rate, which is 5%, 1 plus 0.05, to the power of T equals to 40. Now, if you press your calculator for this, right, you are going to get 351,000, is that correct? 351,999. So it's about 352,000 from an initial amount of 50,000. So this is the beautiful part about compound interest. You basically 7 times your money. So you 7x your money, thereabouts, okay? From 50,000 become 351,000. That certainly beats inflation. Is that all right? Okay, now, state the kind of growth that compound interest provides. So I've stated exponential growth already. Now, is there an investment scheme in Singapore that is similar to that described in part B? Anyone knows? Anyone knows? Huh? Great Eastern. There might be. Yeah, but usually at 5% return, right, it is usually projected. Projected is not that guaranteed. So what is there a guaranteed or almost, you can pretty much say that it's guaranteed 5% return in Singapore? CPF, that's correct. So for part C, actually, right, the answer is CPF. But it's not just normal CPF. It must be your CPF special account. Okay, they call this SA lah. CPF special account on the first 60,000. If I didn't remember wrongly, or I suppose CPF haven't changed this number yet. Okay, the special account on your first 60,000 compounds at 5%, gives guaranteed return. Okay, and I can tell you that this thing is fantastic. Is fantastic, right? You're of course like 20 plus years of age, right? All right, most of you I believe are 20 plus. Okay, maybe 20. Until your retirement age or government supposed retirement age of 65, roughly 65, you have about 40 years, 40. So if you can try your best and contribute, okay, and by the way, you can transfer your money, right? Let's say you work part-time, you teach tuition, okay, maybe you are a YouTuber and whatnot, right? You can take your money, put inside the special account at your age, okay? So if you have, let's say, at least 50,000, you don't need to touch the money. You just wait until you're 65 years old, you're going to have 351,000 or 352,000, roughly, okay? And this is the thing that many Singaporeans, they try and do. Typically, after we start work, okay, we try and contribute. That means we do a transfer, monetary transfer, into the special account. And every year, right, at maximum, we can only transfer about $8,000. Okay? And CPF also very smart, because they know that they give you guaranteed 5%, 4%. Okay, because if your special account above 60K, right, you're going to get 4%. Okay, but that's still not bad. So CPF also under pressure to give the so-called guaranteed return. So which means to say that, right, you can only transfer cash to your special account only up to a maximum of about 200 plus thousand. Okay, then they won't take in already. Because if they were to take in more, which many of us actually want to transfer more so that we can get the guaranteed 4% return, right? They are going to be under tremendous pressure to give us that kind of return. Okay, because it's guaranteed for every citizen. Okay, and including the PRs, PRs also have CPF contributions. Okay, so I hope this is something that I share with you, because you have the luxury of youth. Okay, I don't have the luxury of youth, right? So I'm actually like less than 20 years away from my 65. So I don't have the compounding duration as what you have. So my compounding, if I have the principal, my compounding only until maybe around here only. So you can see the growth here, right? The difference here as compared to the difference here, right, is not linear. It's not linear, right? So the more time you have, it's like, if you have 40 years, I have 20 years. It's not like you have twice the money as me, It's not. It's many more times the money as me. Okay, because it's exponential growth. The later growth is much more than the earlier growth. You must get that. Okay, unless you really like to work. Okay, you really like to work, you embrace office politics, right? You like people breathing down your neck and telling you what to do, then by all means, spend all your money. Okay? Yeah, so just give you a little bit of my own experience with this CPF special account. Hopefully, you make use of your youth. Okay, right. So that will be for question 5. Okay, now I'm going to go through question 6, which is on this thing called the logistic ODE. So actually, I have somewhat introduced this to you before after the derivation of the pandemic, the COVID-19, the pandemic infected population, right? I mentioned that it's exponential, but it doesn't make sense. Well, how can the number of infected, right, just keep on growing exponentially? It doesn't make sense. The Earth, have a finite number of people. So therefore, it is more logical if the growth actually follows this thing called the logistic ODE. Now, what's important about the logistic ODE is that, right, it accounts for a constraint of a maximum. This logistic ODE, very realistic. There is a constraint of a logical maximum. So if it's a pandemic, right, then certainly the maximum that it can spread to is everyone on the planet or everyone in a certain community, assuming the virus doesn't get out of that community. Okay? So therefore, there is a constraint of reaching a maximum. Okay? So now we're going to just discuss, all right, because I didn't get down to deriving this ODE, but we can just kind of deduce, right, from that expression, we can kind of deduce, right, how come it can give us the constraint of having a maximum, okay? So, now you see, so this part A, analyze the ODE and explain what happens when P increases, okay? When P increases initially, so when the population of the infected, just maybe make use of a pandemic or virus spread, okay, easy to understand. So when P is small, because it's increasing, right? Let's say you got only a few persons being infected when P is small. Now what happens to P over M? P over M is approximately 0. Because P is very small, and usually the maximum is usually a big number as compared to the small number in P. So that means P over M, small number over big number, is approximately 0. So when that happens, right, okay, let's put a 0.1 here. Now you're going to get 1 minus P over M is almost 1. So which means P prime is approximately RP. Agree, right? Just a simple magnitude analysis. So if P prime is approximately RP, but that is what? That is the model for exponential growth. So therefore, P grows exponentially. Can Okay? So then you realize that as P increases, P prime is going to be, because 1 minus P over M is no longer close to 0 as P start to increase, approaching M. So 1 minus P over M is going to be less than 1. So if that's the case, right, then certainly P prime will be less than RP. Agree, right? So if P prime is less than RP, it doesn't grow exponentially, right? It's going to slow down. So P grows slower. Agree, Okay? So then let's continue to increase P. 3. So as P increase some more, as P approaches M, because your population infected, right, just keep on growing, right, and it grows towards the maximum, the theoretical maximum. So as it grows towards M, right, what's going to happen? P over M is 1. P over M is going to approximately be equivalent to 1. So that means 1 minus P over M is approximately 0. It approaches 0. Then if 1 minus P over M is 0, then P prime is going to be 0. So what does that mean? That means there is no longer any growth. So P approaches a constant. Because cannot grow already, P prime is approximately 0. How can P grow? Can Okay? So therefore, this is going to give us, right, the S curve that we see in our logistic growth. Okay, so I'm going to give you 3 parts. The first part is the exponential growth part. It happens when P is small. Okay, when P is small, you see exponential growth. Then as P increases, you're going to see that the growth is slowing down. So which means to say that the curve, the curving up, the convex curve, right, becomes a non-convex curve. So that means it grows maybe linear. Then after that, right, then it becomes slower growth. Then final part, right, is when P over M is approximately 1. P is approaching the maximum already. So when that happens, it's going to approach a constant for the population P. Is that right? Okay, so all the 3 different stages, right, has been illustrated on the curve here. So this is called the logistic ODE. Okay, and it's very logical, and it has really been applied, right, to model many growth phenomenon under a certain logical constraint. Okay, so that's for part A. So now solving this ODE for P of T. Solving this ODE. So I'm not going to solve, because if I solve, you have nothing to solve. So therefore, you solve. How difficult is this? Not difficult. This is separable. It is separable, right? P times 1 minus P over M. So this is just a function of P. Okay? So therefore, DIY for solving using the separation of variables. So you DIY. Okay? So they give you the initial condition. So this one must solve for the constant of integration C. So this one you DIY. If cannot, it's okay. Consultation, I will go through during the consultation on Friday. Okay, if you can solve, then well and good. Okay, the answer is here. Can Okay. So let's take a look at part C. Given that P naught equals to 1, R equals to 0.1, right, and M equals to 100, which means that the maximum population should be 100. Okay, maximum population should be 100. So therefore, let's look at the logistic ODE. Maybe this one. Okay. You see, P naught equals to 1, right? That's the initial condition, right? Your maximum is 100, and then the growth rate is 0.1. Okay. So therefore, you can see here. I mean, this is not really kind of a growth rate. It's more of an aggregated growth rate. So therefore, you can see the S curve nicely formed here. Maximum is always at 100, and it fulfills the initial condition, because at the initial condition, right, at t equals to 0, your P is 1. Okay, so this is your very nice logistic curve. Okay? So what's going to happen if you increase the growth rate? Any guesses or not? Just do a quick parametric analysis here. What do you think if I increase? What do you think will happen to the curve if I increase this R? Very good. Okay? Because it's going to grow faster, the growth rate is going to be faster. So it becomes sharper, and it's going to hit the maximum faster, but the maximum will not change. You can see. You see? Can So this is your logistic growth curve. Okay? Which follows, which is in agreement with our part A. Okay? Of course, this has to be somewhat expected, right? What I'm trying to say here is that if, let's say, you do the analysis, but you have your solution didn't turn out to be showing you the trend as deduced here, right? Then you better check your solution, or you better check your analysis in the earlier part. Okay? That means for something that we can imagine, right, that is humanly possible to imagine, it should agree with our intuition, although sometimes it doesn't. Okay, when it doesn't, we have to go back and review again. Because sometimes our intuition is not as strong, right, as what the mathematics can predict. Okay? So it could be the other way as well. Sometimes the math actually predicted something that is illogical. Then we have to use our intuition or experience, right, to correct the mathematics. Okay, so it works both ways. Any questions with the logistic OD? Very good. Now, question 7. Okay, so this one I want to go through with you. Okay, and actually, this question is actually quite, quite nice in timing. Because recently we have, in Singapore, they just announced that we have this vertical fish farm, farming trouts. Okay, we have a vertical fish farm, right, that rears the trouts in a kind of fish, trouts in so-called tanks, okay, enclosures, right? Then of course that is to promote our food self-sufficiency. Okay, we try to be self-sufficient, right, in our food production as far as we can. Obviously, it's not possible. Okay, we still import a lot of food, but at least for this trout or fishes, right, we can do something about it. Okay, yeah. So basically, you're trying to apply a suitable model for the word problem here. So we have a fish farm estimated that enclosure is able to support a maximum of 10,000 snappers. Okay, another type of fish. So the farmer started with 2,000 snappers 2 years ago and realizes that their population has doubled presently. So the farmer is able to start harvesting from the enclosure when the population reaches 7,000. So now we're going to define a math model for the snapper population and then graph your solution. Okay, so certainly because support a maximum of 10,000 snappers, right? And then as biological species go, biological species will grow exponentially if left alone with, of course, ample food sources. Okay, but because the enclosure also got maximum size, the tank also maximum size, right? So it's not possible to grow indefinitely. So therefore 10,000 snappers is a good assumption. Okay? So now, right, since the growth is under a constraint of a maximum, the logistic model is suitable. Okay? So therefore the logistic model, we have derived it here. Okay? I say not derive it, but then we didn't derive the solution, but you are supposed to go and derive the solution. Okay? So the solution, right, is given by this number. It's given by this function. So therefore, the solution or the population of snappers is this P of t. So this is the function. Okay, but we can plug in some parameter values. So P naught, right, so it says that 2 years ago. Okay, so 2 years ago, we can take that 2 years ago as the initial condition. So 2,000 snappers 2 years ago. So this guy is let P naught, let the initial condition, P of 0 equals to P naught, and this is equivalent to 2,000. So we plug in that 2,000. Then the maximum is 10,000. Okay? Then after that, over 2,000 plus m minus p naught. But m minus p naught is just 8,000 because 10,000 minus 2,000 what? So it's 8,000 times e to the minus rt. Following? Can Okay. So therefore, if you observe, right, this equation is just 20,000. Okay, maybe do step by step. So you can see the 2,000 here, so it's factorize out 1,000. Okay, factorize out the 1,000, factorize out 1,000 from the... Okay, so factorize out 1,000 from the numerator and the denominator. Therefore, you're going to get 20,000. 20,000. Okay, maybe let me strike off the thing here. So 2,000, this one factorize. So you're going to get 20,000 over 2 plus 8 e to the minus rt. So this is our model. But we have a problem. We do not know what is r. So how do you suppose we can find r? Similar to the problem just now. How to find r? Well, we have a condition, right? Correct or not? So it says here that the population has doubled presently. So that means after 2 years, the population becomes 4,000 what? So we can make use of that known condition to find R. Okay? So let me underline that particular condition. So that condition is population has doubled presently after 2 years. You must understand that this is 2 years ago. So we are like going back in time, right? And put this as the initial condition at t equals to 0. That is 2 years ago. So therefore, double presently means, right, after 2 years, t equals to 2. So your population becomes 4,000. So to find R, use P of 2 equals to 4,000. Because double presently, after 2 years already. So therefore, we just plug in the values. So P of 2, right? Okay, so I straight away write here. So this is equivalent to this number. Then you feed the t equals to 2 into the expression. Is that right? Okay, so I'm not going to solve. You should know how to solve. So therefore, you are going to solve to get R equals to 0.49. Okay? So certainly, once you have the R value defined, right, then your P of t is fully defined. So this is your fully defined solution, okay, with the R being 0.49. So therefore, with this, you can actually use it to make predictions already. So now the farmer is interested to know, right, under this particular model, when can he harvest his snappers? That means can sell for money. Okay? So therefore, that happens when your population reaches 7,000. Okay? So you want at P equals to 7,000. Then you solve for T. Equals to this. Solve for T equals to. So what's going to happen is that you're going to be able to solve for this number, which is 4.5. So you must understand that 4.5 years is taken with reference from 2 years ago. So therefore, it is another 2.5 years. Then the farmer can start to harvest. Okay? So this 4.5 years is reference from 2 years ago. Reference. Any questions? Any part that you need me to re-explain or reiterate? Anyone? Good. So, yeah. So keep in mind that if you don't have a constraint or a maximum, right, you're going to get the exponential growth model, right, which is basically just P equals to RP. Right? But if you do have a constraint of a maximum or theoretical maximum, okay, as most things on Earth, right, will experience some finite bound, then you should use the logistic growth model. Okay? So this is for question 7. So you can see the past year question here, which I will not go through. You will try first. Okay? Yeah, by the way, you might have noticed that actually this ODE, right, looks similar to the one that we previously derived, okay, for our teacup with heater problem. It's just I changed the Q over MC to P of T over MC. Okay? So certainly there's only so much I can change, right? So just be well versed with the different kinds of heat input and heat output terms, right? And I think you should be fine. Okay? So this is just applying the same kind of conservation of heat energy, right, to the cooling of a battery in a PMD, okay, electric scooter here. So certainly you have the airflow cooling because as you ride the scooter, the airflow is going to flow past the batteries, and typically the batteries is going to heat up, and then you're going to have some kind of cooling fins, right, or of cooling structures, right, they allow the airflow to take away the heat more effectively. Okay? So therefore, applying the conservation of energy, of heat energy to the battery, right, you should be able to get this IVP. Okay? That means IVP means ODE, ODE plus initial condition. Okay? So you do have to also state the initial condition. Okay? You notice that the initial temperature of the battery is at the surrounding temperature Ts, right? So therefore, this gives the initial condition. Okay, make sure you state that. So that's for part A, derivation. Okay, so I leave you to try. Then after that, part B, you can see that now this is a little bit more difficult because the power that is generated when you have full throttle of the skate scooter, okay, of the electric scooter. So when you ramp up the full power, full throttle, right, that heat is going to get generated based on this function. Okay, and this is a logical function because initially when you ramp up, the heat is going to slowly ramp up fast. That's why you see the exponential term here. Then, but after a long enough time t, right, it's going to hit a maximum heat generation Q. Okay? So therefore, you substitute this P of t into this expression, this ODE, and you are going to be able to solve. Okay? So because when you put P of t as that function into the ODE, you are going to get a linear equation. It is not separable. It is linear. So if it's linear, you have to use what? Integrating factor method. Okay? So I leave you to try this out yourself, and you're going to get this solution. Okay? This solution, right? Yeah, then after that, part C, okay, part C is actually for last year where they can still use the laptop. Okay, but you guys cannot use laptop, right? So therefore, you will still be asked some questions regarding the solution. How are you going to interpret, right? And how does it so-called apply in the context of the problem? Okay, because as the designer of this electric scooter here, right, we want the heat of the battery or the temperature of the battery, right, to stay below a certain safety limit. In this case, 60 degrees Celsius. Okay, because as you know, there are many explosion or burning cases of scooters, right, catching fire. Right, so therefore this is an important consideration. Okay, so with that, I have covered that is necessary for this tutorial 3 today. So this one you try first. If any problem, next Friday, we will go through. Okay? Questions? I'm done for today. So think about, maybe you review through whatever I've gone through today while I will mark your attendance. Alexander, Aliyah, Emelina, Angelico, Sean, Brian, Chen Chang, Zhen Yi, Ivan, Yang Ing, Emilia, Erwin. Erwin, you're here. You're not here for the lecture. Yanjing, Zhan Yang, Dongping, Noritetsu. No, he's not here today. Xavier, Joey, Jordan, Kayla, Kevin, Ken Leong, Sharon, Dawson, I thought I saw him. Dawson, he went back. Chen Ying, Jonathan, Kun Yong, Mac, Mikhail, Mohan, Azari, Danish, Irfan, Naya, Bingjie, Keng Hong, Zixuan, Fadila, Phoebe, Yan Heng, Sherwin, Benjamin, Raymond, Reese. That's how you pronounce, is it? Ruji Ratanarai, Jumpang, Jerome. Hey, you're not here for lecture. Sean, Justin, Papo, Ryan, Sohadi, Johans, Weiyan, Yi Zhong, Tamsin, Trisha, Yang Hong, Shi Kang, Xing Zhi, Zotet, Zumping Y. Okay, any questions or not on the tutorial 3? No? Okay, so I wish you all the best in your revision. So I'll make an announcement on X side on the consultation class. Please try the questions that I didn't do. And I ask you to try. Please. Don't give me heart attack when I mark your midterms, please.